All right, welcome, and thanks for making the time. The title of this talk is The Cat and Mouse Game of Infrastructure Cost versus P99 Latency. I'm Parak. I run DevOps at the New York City office of Tvili, which was recently acquired by Nebius. Before we get into it, I want to set expectations up front. This is a talk about trade-offs. There's no silver bullet at the end. If you're hoping for one weird trick that makes your inference stack cheap and fast and reliable all at once, you can drop off now and I won't be offended. What I'm going to try to give you instead is a mental model, diagnosis, and a small set of patterns that have actually held up in production for us. The title is a little cheeky, but I think it's accurate. Every time we shave off a tail latency problem, the cost curve moves. Every time we squeeze costs down, latency creeps back up. It's a chase. And the goal of the next 30 minutes is to help you play that chase with your eyes open, because most teams I talk to are playing it blindfolded. Before I start making claims, a quick note on where I'm coming from, because context matters for a talk like this. I've spent years working on infrastructure and reliability in latency-sensitive environments. My first stop was Capital One Car Tech, where slow pages is annoying. It's a lost transaction. It's a regulatory footnote, a customer service call. You learn that very quickly that latency is a dollar figure. And after that, I was at FanDuel working with sports betting. If you've never operated a sports book during the Super Bowl, imagine it's like Black Friday, except it happens over a 20-second window at the end of the fourth quarter. And if you miss that window, you just lost millions of dollars in revenue. The Super Bowl is a literal load test, and P99 is the difference between a bet getting placed before the whistle and a very angry customer. Now I'm at Tvili. We were recently acquired by Nebius, and we're building the web infrastructure layer for AI agents. This is like the connective tissue that lets agents search, retrieve, and act on the open web at scale. So across all three stops, common thread, latency-sensitive systems where business genuinely cares about the tail in dollars. Here's the plan for the next 30 minutes or so. 3 chapters. Chapter 1 is the problem. I'm going to convince you, if you're not already convinced, that tail latency is the thing that actually matters, not the average, and that fixing it is disproportionately, almost unreasonably expensive. Chapter 2 is where the money hides. I'm going to open up a modern inference request and show you 4 specific places in the stack where your cost versus latency trade-off is being paid for, whether you see it or not. Chapter 3 is the response, 3 patterns that have worked well for us, plus a scoreboard, a way to evaluate any architectural decisions going forward, so you're not just optimizing one axis while silently trashing the other 2. By the end, you should walk away from this call with a mental model, like a diagnosis for your own stack and a prescription you can start applying on Monday. So let's get right into it. Chapter 1, the problem. Now, this is the part where a lot of infra talks just show you a P99 graph and expect you to nod along. I'm going to be doing a little bit more than just that because I think the problem is broadly misunderstood, even by teams who think they understand it. The thesis for this chapter is simple. The problem you think you have probably isn't the one that's actually costing you money. So here's the frame. When most teams talk about AI infrastructure performance, they talk about averages. What's our P50? What's our average cost per request? How fast is the model? And those are fine numbers to know. They're just not the numbers that determine whether your product is good or bad. The thing that determines whether users love you or hate you isn't the average case. It's the worst case they encounter often enough to remember, which is the tail, the slowest 1% of requests, maybe even 5%. And for latency sensitive products, the tail isn't a technical nuisance you can file under future work. The tail is the product. If your P99 is bad, it genuinely does not matter how good your P50 is, because every user with any volume is going to hit that P99 regularly. And that's the experience they're going to remember. The median is the experience you advertise, and the tail is the experience people actually have. Now, let me make this concrete with real numbers. The distribution on this slide is from one of our endpoints from last quarter. I rounded things slightly, but this is data. P50 sits at 180 milliseconds. Feels great. In a demo, this is pretty snappy. P95 already at 850 milliseconds, and P99 is almost at a second and a half. That's an 8x gap between median and the tail. Now, here's the kicker. This is the part that people miss. If your product does not kind of fan out, there's no checking or agentic looping, your effective latency is dominated by the tail, not the median. Say you make let's say you make 3 synchronous calls to the endpoint. The probability that at least one hits the P99 approaches 1 very quickly. Your user experience is essentially the P99 of the P99. The math compounds against you. So when someone on your team says the average looks fine, what they're really telling you is, I haven't looked hard enough. They're showing you the number that's most comforting, not the number that matters. And before we move on, I want to push this just one step further, because even this chart understates the problem. A per call distribution is the wrong unit. The unit that matters is per session. And if you do the math on what happens to a user across a session, the picture gets significantly darker. Now, if the distribution wasn't uncomfortable enough on its own, let's talk about what this actually means for a real user. In a real session, because a P99 of 1% sounds like a small problem, 1 in 100, who cares? But the unit of experience for a user is not a single call. It's a session. An agent session might make 20, 50, 100 calls on their behalf. So the real question is, what's the probability that a user over a course of a session hits the tail at least once? The math here is unforgiving. With independent calls, it's a 1 minus 0.99 to the n. For 20 calls, you're already at 18%. Almost 1 in 5 sessions see a stall. For 100 calls, which is not a crazy number for an agent, you're at 63%. Most of your users are hitting the tail. The tail stops being a rare event and becomes the default experience. And remember, this is independent events. Real inference tails are correlated. A slow pre-fill cascades. Pause affects every request in flight. So the real numbers are worse than this curve. This is the optimistic chart. When someone tells you P99 is only 1%, they're describing a per call number and quietly hoping you apply it to per session experience, and you shouldn't let them do that. Okay, so we get it. The tail hurts. Obvious question, let's just throw some money at it. And here's where the talk gets a little uncomfortable. The relationship between latency and cost is not linear. It's more like exponential on the expensive side. Going from 500 milliseconds to 300 might double your infrastructure bill. Going from 300 to 200 might triple it again. Going from 200 to 150 is where engineers start doing some genuinely reckless things. Over provisioning GPU 2 or 3 times over, keeping hot spares idling permanently, disabling batching, pinning memory. Each of these moves the needle a little bit, but it adds a 0 to the monthly invoice. Now, this curve right here is the single most important mental model in this talk. If you forget everything else, remember the shape of this curve. Because if fixing the tail is this expensive, we need to know exactly where the money is going so we can fix it with intention and instead of panic. Chapter 2. This is where the money hides. This is the diagnostic chapter, and here's how I want you to think about it. We're going to open up a single inference request, watch it end to end, and figure out where the time goes and figure out where the money goes. And it turns out those two things are related, but they're not the same thing. And then I'm going to give you 4 specific hiding places where all the interesting cost versus latency action happens. By the end of this chapter, if you go back to your own fleet, you should be able to just point at your dashboards and say, okay, my problem is pattern number 2, or I'm fighting pattern number 3 this week. This is a diagnosis before prescription. Okay, so let's follow the clock. This is one of the most underappreciated facts about modern inference. And a typical request, and this varies a little by model family, of course, but not as much as you'd think. Only about 20% of the wall clock time is actual GPU compute. 20. The other 80% is everything else. Is like queuing in front of the model server, tokenization, pre-fill, KV cache lookup and management, memory allocation, network round trips, serialization on the way out. When someone on your team says, "Oh, the model is slow," what they almost always mean, even if they don't realize it, is everything around the model is slow. Your optimization work, if you want to be honest about where the wins are, lives in that 80%. And importantly, so does most of your spend. You're paying for a GPU for the full wall clock time of the request, even if the 80% where it's not actually computing. So every millisecond we can shave off the overhead is both a latency win and it's a cost win. And those are the best type of wins. All right, narrowing it down. I'm going to give you 4 specific places where the money hides. These aren't the only places, but in my experience, this is where the big money is. Number 1, auto scaling overshoot. This is capacity that stays warm long after the spike that warranted has passed. This is number 2. This is GPU underutilization. Paying full rate for a H100 that's running at 40%. Number 3, batching trade-offs, an optimization that looks great on a throughput chart and quietly destroys your tail. And number 4, the tail itself. 5% of requests eating a disproportionate share of your fleet capacity. We're going to walk through each of these. And the important thing to understand is the right fix depends on which one is hurting you most. You can't just apply all of them blindly. Some of them conflict with each other. And this is taxonomy, not a checklist. Autoscaling. Number 1, let's talk about why this is so hard for AI workloads specifically. Autoscaling is at its core a reaction time tax. By the time your metrics pipeline has noticed a spike and processed that signal, the spike is already hurting users. That's what, 10, 20, 30 seconds of an elevated P99 just right there. By the time your new replicas are warm, and for a 70 billion parameter model, warm means minutes, not seconds. You're pulling weights, warming the KV cache, doing dummy passes. And by the time they're actually ready to serve, the spike is often over. So in practice, teams do one of 2 things. Either they scale aggressively and eat the idle cost, which is most of what you see out there, or they let the tail stretch during spikes and they just start praying. Neither is great. Neither is honestly even good. Autoscaling built for stateless web services is fundamentally mismatched for stateful, warm-up heavy GPU workloads. Number 2, GPU utilization. Now, here's an uncomfortable truth. Most inference fleets, in my experience, and from talking to peers at other shops, run somewhere between 30 and 50% GPU utilization in steady state. This is not during a lull, this is steady state. Your instinct, if you're from a CPU fleet background, is to see that and say, "Oh, we're wasting half our capacity. Let's pack it tighter." And I'm telling you, please do not do that. Queuing theory is absolutely merciless here. The moment you push utilization past 60, 70%, the wait time in front of your model server doesn't grow linearly, it grows vertically to infinity. As utilization approaches 1, queue depth approaches infinity, and that's just math. That's not a bug. It's not a config you can tune around. So we intentionally leave headroom, which means the real thing to internalize is roughly half of every GPU dollar you spend is not buying you compute. It's buying you latency insurance. It's buying you slack against the queuing curve. And that's the ceiling on how efficient you can get without doing something architecturally clever. Number 3, batching. This is the optimization every engineer reaches for first, and it's the one that most often backfires in subtle ways. The intuition is correct. Bigger batches means better throughput per GPU second, which means better cost per token, and that's true. What's also true, but less intuitive, is that batching is fundamentally at odds with latency. A request that arrives at the start of the batch window has to wait for the window to fill for over a time to fire before it even starts being processed. Continuous batching, this is like iteration level scheduling where requests can join an in-flight batch, helps a lot, but it doesn't eliminate the trade-off. It just softens it. The honest framing is this. Batching trades median latency for tail latency. So you get a tighter median and a longer, fatter tail. Now, whether that's a good deal for you depends entirely on your product. If you're doing bulk embedding, that's great. Batch hard. If you're serving an interactive agent loop, you need to be much more careful about how aggressive you are. Now, concretely for us, we had a background embedding pipeline and an interactive search endpoint sharing one model server, and we tuned batching for throughput on the embedding side. Then someone asked why the interactive P99 had doubled. It was because an interactive request can now get stuck behind a 64D batch of embeddings. This is one knob, two workloads, completely incompatible SLOs. The fix wasn't better batching, it was splitting the feet. It was splitting the fleet, which is a preview of pattern 2. And now the fourth hiding place, the one that makes all three of the others worse. This is the tail eats itself. This is the most important dynamic in the whole chapter, and I want you to sit with it. A slow request holds a slot on your GPU. That slot isn't available for the next request, which now has to queue. The queued request now has a bad latency too, even though nothing was wrong with that request intrinsically. One hiccup becomes a wave. One slow prefill causes 5 downstream requests to miss their SLO. Correlated tail events compound this. They don't average out. Your tail is not an independent sample, it's a feedback loop. This is why the worst minute of your day always looks so much worse than your monitoring thinks it should be, based on average volume and average latency. This is also why paging on averages is nearly useless. By the time the average moves, you're already in crisis. Now, let me make this concrete with the 3 in the morning story, right? This is classic. We had a 10-second stall on one replica, 1 out of 40. Normally, 10 seconds on one replica is forgettable, except that replica was holding live requests. Now, those requests have timed out. The client retried. The retries are landing on healthy replicas, which now have double traffic. Those replicas start queuing, queue depth rose, latency rose. More clients are retrying. Within 90 seconds, a 10-second blip on one box had turned into a fleet-wide P99 excursion that took us 15 minutes to recover from. That's the tail eating itself. One hiccup, a cascade, a retry storm, a 20-minute incident, and none of that shows up in an average view. The average over 90 seconds of 40 replicas barely wiggles. And now, okay, we have the diagnosis. These are the 4 hiding places. We have chapter 3, the response. This is the prescriptive chapter. I'm going to give you 3 patterns that have worked for us, and then a scoreboard. This is going to be like a way where we can like evaluate any decision going forward. I want to be clear about what these are and what they aren't. These are not silver bullets. These are trade-offs. But trade-offs where the math is on your side instead of against you. Each one moves you to a better point on the cost latency curve than where you were before. You don't have to pick one, but you should probably do all 3 eventually. But start with whichever one maps to the hiding place that's hurting you most. Okay, first, before we get into the patterns, we need to acknowledge something. The old playbook is broken for this world. The old playbook is this. It's provision for the peak, scale on request rate, alert on the averages, treat the fleet as mostly homogeneous. And that playbook works beautifully. And that was when a request cost a fraction of a cent. You could over provision a web tier and it showed up as a rounding error. An inference request can cost 20 cents, 600 times more. So over provisioning a web tier is annoying. Over provisioning a GPU tier is a budget emergency that shows up in a board meeting. The cost structure of what we're running is just fundamentally different, and the operational patterns have to change to match. If you're running your inference fleet with the same playbook you used for your monolith 5 years ago, you're losing money every single day, and you don't even notice. All right, so here's pattern 1. Hedged requests. The idea is this. If a request is about to hit the tail, if it's been in flight for, say, the P95 duration and hasn't come back yet, you fire a duplicate request to a different replica, and take whichever one comes back first. Now, you're probably thinking that sounds expensive. Like you're doubling your traffic essentially, but you aren't. This isn't what that is, because you're only hedging the slow tail, and the slow tail by definition is a small fraction of your traffic. This is just a few percent. So you're paying a few percent more cost for a massive improvement on the tail. Now, Google actually published a paper on this in 2013. It's called The Tail at Scale by Jeff Dean and Luis Barroso. This is one of the best distributed systems papers ever written. And the technique is still underused more than a decade later. For us, implementing hedged requests on our slowest endpoint cut P99 by about 35% at roughly 3% additional spend. This is a ratio you almost never see in infrastructure work. Pattern two, this is tiered serving. So this is probably the single biggest lever most teams aren't pulling, and it's the one that changes the shape of your cost curve the most. The insight is not every request deserves your best model on your best hardware. In fact, most of them don't. Route your latency critical requests, this is like the interactive ones, the user facing ones, to a hot, over provisioned tier that pays for the headroom, and route your standard traffic to a warm, moderately utilized tier, and route your batch tolerant traffic. This is like overnight jobs, background enrichment, anything where like a 10-minute delay is fine. Route that to a spot priced, preemptible, aggressively batched tier that can soak up the cheap capacity no one else wants. This is 3 tiers, 3 SLOs, 3 cost curves. And the magic of this is you get to optimize each tier for the one objective instead of trying to hit a compromise on a single fleet. Now, every team I know that has implemented tiered serving has cut their total costs by like 20 to 40% with no regression in user visible latency. Here's pattern 3, feedback given auto scaling. This is the one that fixes the auto scaling problem we talked about earlier. So stop scaling on CPU, stop scaling on request rate, stop scaling on anything that's a proxy for the thing you actually care about. Scale on your signal that is the thing that you care about. This is queue depth, or even better, projected P99. Your autoscaler should be reading the same signal that your users feel. We moved from request rate based scaling to queue depth based scaling last year, and the end result, over provisioning dropped by 22%. No SLO regression, and if anything, marginally better tail behavior because we were scaling on the actual leading indicator of user pain. And as a nice side effect, our page volume dropped about 60% because autoscalers that react to the right signal stop waking people up at 3 in the morning for spikes that would have self-resolved. All right, I just pitched you 3 patterns and told you each one is a big win. I want to spend a minute on the other side of that story because if I left it there, I'd be doing exactly what I warned you about in chapter 2, showing one axis and hiding the rest. Each of these patterns has a failure mode. I've hit all 3. So pattern 1, hedging. The failure mode is firing the hedge too eagerly. If you trigger on P75 instead of P95, you're not hedging the tail. You're duplicating every request, and your cost spikes 40 to 60% while your tail barely moves. The fix is to trigger high and to cancel the loser the moment the first response lands. So you're paying for the duplicate only for the few hundred milliseconds that you actually needed it. Pattern 2, this is tiered servicing. The failure mode is silent downgrades. So your interactive tier fills up during a spike, traffic spills over into the batch tier, and suddenly your user-facing requests are queued behind overnight jobs that have a 10-minute SLO. The user never sees the downgrade happen. They just see their chat interface spin. So you page at 3 in the morning. The fix is in admission control at the tier boundary. Shed load before you cross pollute tiers. Pattern 3, feedback-driven auto-scaling. The failure mode is thrashing. Queue depth scaling without hysteresis flaps. Scale out, the queue drains, scale in, queue builds, scale out again. All this flapping costs you multi-minute warm-up on a 70 billion model. Your autoscaler becomes the incident. The fix is asymmetric cooldowns. So this is scale out fast, scale in slow. And I'm telling you all this not because I want to talk you out of these patterns. I'm telling you because the difference between these patterns working and these patterns burning you is about, what, 200 lines of config. The ideas are right, the defaults are wrong. So you got to tune them. Okay, so now you have these patterns. How do you decide which to apply first? And more importantly, how do you evaluate any future proposal that comes across your desk? Here's that scoreboard. 3 axes: cost, latency, reliability. You cannot maximize all 3 simultaneously. They fundamentally trade against each other. And that's basically the thesis of this entire talk. Every single architectural decision is a point in this triangle. And the mistake I see teams make, honestly, and this is the same mistake that I've made, is optimizing one axis in isolation and not reporting what happened to the other 2. Someone walks into a review and says, we cut costs 30%, and nobody asks what happened to the P99 or to the error rate. Or someone says, we dropped P99 by a half, and no one asks about what it cost and about, reliability. Going forward, every proposal, every experiment, every architecture review, demand all 3 numbers. And if someone only gives you one, they're probably hiding the other 2, whether they know it or not. Okay, zooming out for a moment, I want to leave you with a bigger idea than any of the individual patterns. The shift I think we're all moving towards is adaptive infrastructure. The future isn't a bigger cluster, it's a smarter cluster. One that knows when to sprint and when to rest. One that spins up aggressively when the traffic shape changes, not just when the volume changes. Spins down aggressively when the shape stabilizes, and routes by workload character, by request type, by user tier, by SLO, instead of just by a round robin. That treats cost and latency as a joint optimization problem, not 2 separate KPIs that 2 different teams are responsible for. We're not there yet as an industry. No one is really. But the teams that get there first are going to have a structural cost advantage that compounds month over month. And it's not a 10% advantage, it's a 2x advantage. And this is worth paying attention to. Okay, we are at the end. 3 things to take home, and then I'll let you go. 1, measure P99, not P50, and watch the ratio. This is not just the absolute number, because the ratio tells you whether you have a tail problem or an everything problem. 2, the cost latency curve is not linear. So know when you're on it before you start optimizing, because the right move at 500 milliseconds is the wrong move at 200 milliseconds. And 3, build for adaptation, not for the peak. The fleet you design for the traffic you had is going to lose to the fleet that reshapes itself for the traffic you're about to have. Now that's it. Those are the 3 ideas I hope you take back to your teams. Thank you for spending the last 30 or so minutes with me. I know attention is the scarcest resource at a summit like this, so I genuinely appreciate it. I'm Parag, Senior DevOps at Tivili, now part of Nebius. If any of this resonated, or better, if you've built something smarter than what I described, I would genuinely love to hear about it, especially if you disagree with any of this. I learn more from the arguments than the nods. So you can find me at parag.juggy on most platforms, or drop me a note at parag.juggy@tivili.com. I read everything. So thanks again, and I appreciate you all.